Hello, in this C programming video, we're going to be demonstrating a first in, first out scheduling policy. The program we're going to do in this video demonstrates the implementation of a non-preemptive first in, first out scheduling algorithm for a set of periodic real-time tasks. Our simulation is also going to use a single discrete integer-based clock, which we're going to use current time, managed by the main thread to ensure precise sequential event logging. If these types of long-form example videos are informative, please give them a like and comment with any questions or thoughts, as well as video ideas, and subscribe to the channel to get more videos like this. So let's get started. First, we need to include our libraries. We're going to be using 5 libraries in this program. Our first one is going to be our standard input-output library. Next is going to be our standard library. Our third library is going to be our pthread library. Fourth is going to be our Unix standard library. And then finally, our fifth library is going to be our string library. So now that we have that done, the first thing we need to do is to define our constants and data structures. First is going to be the number of tasks that we're going to have. So we're going to have 3 in this program. So we're going to use the define keyword, and then we're going to call this num_tasks, and we're going to make that 3. Next, we need to define the amount of times that each task is going to repeat, or cycles. So we're going to use define again, and then we're going to call this num_cycles. And in this example, we're going to do 4 cycles. And then the last thing we need to define is the number of total jobs. So we're going to do define total jobs, and that is going to be equal to the number of tasks multiplied by the number of cycles. Next, we need to define the static parameters for the 3 tasks. So this is going to be a 2D array with 3 rows and 4 columns holding the static task definitions. So we're going to use, this can be constant, it's not going to change. Constant int, we'll call this task params. And then again, the first dimension is going to be number of tasks. And then each task has 4 traits. So what are those? They're going to be offset, deadline, burst, and period in that order. Offset is the number of seconds it takes after the time equals 0 for the first task or the first cycle of that task to arrive. The deadline is how long from the arrival time do you have to do it. Burst is otherwise known as execution, is the amount of time that the task actually takes. And then the period is the difference between the amount of times between the arrival of task I and task I plus 1. In this example, for simplicity, I'm going to have the deadline and the period be equal. So our first task, now we can actually define it now that we understand. Our first task has an offset of 0, a deadline of 6, a burst of 2, and then a period of 6. Again, we're talking about seconds here. Task 2 has an offset of 1, a deadline of 8, a burst time of 2, and a period of 8. And then finally, our third task has an offset of 2, a deadline 15, a burst of 4, and then a period of 15. And then the next thing we need to do here is to define the basic structure representing a single job. So we're going to do that with type def struct. And then there are quite a few things we need to define in this struct. First is our task ID. Next is our cycle ID. Third is our job name. So we're going to do store that in a sequence of characters. And then we're going to allocate 8 characters for that. Fourth is the burst time. Fifth is the deadline. And then the last 3 are going to be scheduling metrics measured in discrete simulation seconds. So we're going to use the long data type for these 3. First is theoretical arrival. The second one of these is the start time. And then the final one is the finish time. And then we're going to call each instance of this struct just a job. The final constant we need, the final constant in data structure we need is a global lock mechanism used to prevent the print statements from overlapping. So we're going to do pthread mutex t, and we're going to call this print mutex. So again, as we review here in our constants and data structures, first we need to define the number of tasks. Then we need to define the number of loops or cycles. Third, we need to calculate the total jobs. And then in our constant array here, we're defining the static parameters. And then each array in the array has the values for T1, T2, and then T3 respectively. And then in our struct here, we need to represent a single job with a task ID, which is which task it belongs to. So it's either going to be T1, T2, or T3 in this program. Cycle ID, which instance is it? So is it going to be the first, the second, the third, all the way to the nth instance? But again, in this case, we're going up to 4. The job name is going to be a readable name for console output mainly. The fourth metric here is the burst time. So the number of seconds it takes to run. Fifth is the deadline. So the relative time the job must finish by. Then the theoretical arrival is the first of our scheduling metrics. And this one is going to note the exact time the job is ready. The start time is going to be the actual time the scheduler lets the job begin. And then the finish time is going to be the actual time the job completes execution. And then finally, in our constants and data structures, this pthread mutex is going to be a global lock used to prevent print statements from overlapping. So now that we have our constants and data structures out of the way, we can now move on to our helper functions. The first one of these is going to be a way to compare the two jobs based on their theoretical arrival time. So this is going to be an inf return type because we're going to be returning task ID. We're going to call this compare jobs. And then inside, we're going to pass in a constant void pointer A and a constant void pointer B. So inside the function, the first thing we need to do here is to cast the generic void pointers back to the specific job type. So we're going to define one job pointer called job A, and that is going to be equal to casting A to the job data type, and then a very similar thing with B. Job B is equal to job casting B to a job variable type. So the first sorting criterion is going to be the arrival time, because again we're talking about first in, first out. So if job A's theoretical arrival, if that is not equal to job B's theoretical arrival, we're going to return the difference. So if A arrives before B, A comes first, being a negative result. So we're going to return job A's theoretical arrival, and then we're going to subtract that. We're going to subtract B from A. And then the secondary sort criterion, so if there's a tie, we're going to just use the task ID to make it consistent. So we're going to return job A's, not theoretical arrival, but task ID, and then we're going to subtract job B's from A. So again, as a review here, in our first helper function, we are passing in two void pointers, so we need to cast job A, and then we also need to cast job B. And then our first sort criterion is arrival time. Because of the first in, first out. And then if that's the case, we want to return the difference of theoretical arrival time. But otherwise, we're just going to return the difference of the task ID. So now that we have our compare jobs function, our second and final helper function is going to be actually simulating the execution of a single job. So this is going to be a long return type because we're going to be returning the finish time. And then we're going to call this function execute job non-preemptive. And then we're going to be passing in two variables. We're going to be passing in a job pointer. And then we're also going to be passing in the current time. So the first thing we're going to do here is actually record the actual start time as the current discrete time. So we're going to make job start time. We're going to make that equal to the current time. Next, we're going to calculate how long the job waited since its arrival. So we're going to store that in a new long variable called wait time. And we're going to make that equal to the start time minus the theoretical arrival. And then now we can output the start event. So we're going to use the printf statement here. And then we're going to use this pre-made text. And then we need to notice I'm using a couple format specifiers. So the first one, the string, is going to be the job name. The second argument is going to be the start time, which we calculated on line 58. And then the burst time. And then finally, the wait time. And then now we're going to simulate the CPU burst time. So the main thread is going to pause here for the duration. So obviously we're going to use sleep. And then what are we passing in? Well, we're just passing in the job's burst time. Then we're going to calculate the finish time based on the discrete clock. So job finish time, we're going to make that equal to the start time plus the burst time. And then we're going to return the finish time. So again, a review here, we're passing in the function, we are passing in the job in question along with current time. And then for the latter parameter, we are immediately using that to store the current time into the job's start time. Then we are calculating the wait time because again, the start time is not necessarily equal to the theoretical arrival, as you will see. Then we're notifying the user that we're getting started. And then next with the sleep function, we're actually simulating the task. Then we are finishing on with calculating the finish time and then returning the finish time. So now that we have both of our helper functions done, we're going to move into our main simulation. So we're going to use int main and then return 0 at the end, as we always do to exit success. But there's obviously a lot that we need to do first. So the first thing we're going to do here is print the simulation header, just so we can see in our program. And then I'm just also going to display the number of cycles and then the total jobs. And then I'm going to say that the jobs are processed based off their global arrival time, which follows the first in, first out principle. First thing we're going to do, though, in our main is we're going to declare an array that hold all 12 job structures. So we're going to do job, jobs, and then this is an array of size total jobs. Next, we're going to declare a mutex variable, though its use is simplified here. So pthread mutex t, and then we're just going to call this print mutex. Next, we're going to initialize the mutex and job array. So we always want to do an if statement to check for errors here. So we're going to do if pthread mutex init or initialize, passing in the address for the print mutex, and then null because we're using default attributes here. If that is not equal to 0, then there is an error. So we're going to use the p-error function to inform the user that there's an error. And then we're going to return 1 for an unsuccessful execution. But assuming the mutex was initialized successfully, we can start by first creating a job count, which is a counter to track how many jobs have been created. So we're going to initialize that to 0. And then next, we're going to loop through each of the 3 tasks. So we're going to use a for loop here. So for int, I'm going to use t. Int t equals 0 for task. T is less than num tasks. And then incrementing t. First thing we need to do here is to actually extract our the four parts of a job. So it's offset, deadline, burst time, and period. So we're going to just use the letters respective. So int o, that is going to be equal to task params t0. Next is going to be int d for deadline. That is going to be equal to task params t1. Int b for burst time is going to be equal to task params t2. And then finally, int p for period is going to be equal to task params t3. Next, we need to loop through each of the 4 cycles. So k equals 1, 2, 3, and 4. So we're going to do for c for cycle, I guess. Int c is equal to 1. And then c is less than or equal to num cycles, c++. And then we're going to first get a pointer to the current job slot in the array. So we're going to declare a variable called job. So job pointer called job. And that's going to be equal to the address of jobs, the jobs array, at the job count. Next, we're going to assign the task ID. So job task ID. We're going to make that equal to t+1 because we don't want to start counting at 0 here. We're going to start at 1. Next, we're going to assign the cycle ID. We're going to make that equal to c, or index. And then next, we're going to format the name as IK. So, example, the first cycle of task 1 is going to be job 1.1. And we're going to use snprintf. So we're going to pass in the job name. Then we're going to pass in the size of the job name itself. Then we're going to pass in our string. Then we're going to pass in the task ID. And then finally, we're going to pass in our cycle ID. Then we're going to calculate the theoretical arrival time. So using 0 plus c minus 1 times p. So the theoretical arrival of the job is going to be the long, not 0, but of O, plus the long version of c minus 1 times the period. And then we're just going to copy the burst time. Then we're going to copy the relative deadline. And then we're going to move to the next job slot. So just going to increment job count. So now that we're done with our both our outer and inner for loop here, the next thing we're going to do is sort all the jobs by the arrival time. So we're going to do qsort jobs. So again, our jobs array. We're going to then the total jobs, then the size of a job, and then we're going to call our compare jobs function. Then we're going to print that we have generated and sorted the jobs. And again, we're just going to pass in our total jobs here. And then now we can move on to the actual execution loop, or the scheduler. So we're going to initialize our current time. That's going to be 0. And then our job index, we're going to store in an integer, and that's also going to be initialized to 0. So we're going to loop until all, in this case 12, generated jobs have been processed. And so we're going to do a while loop. So while the job index is less than the total jobs, because we're starting to count 0. So inside this while loop, the first thing we're going to do here is we're going to declare a job pointer being the current job. So job, current job. We're going to make that equal to the address of the jobs array at the job index. Next, we need to get into our scheduling decision. So we need to check to see if the next job in the queue has arrived. So we're going to use an if statement here. If the current job's theoretical arrival time, if that is not equal, but rather less than or equal to the current time, the job has arrived and is ready, so the CPU is going to execute it immediately. So first is our log. We're going to log the arrival event. So we're going to use printf, and then we're going to just pass in the current job's job name. We're also going to pass in the current job's task ID, and then finally we're going to pass in the current job's theoretical arrival. Next, we're going to actually execute the job, blocking the main thread for its burst time. So, again, remember, this has a return type of long, which is our finish time. So we're going to declare a long variable here called finish time. And we're going to make that equal to execute job non-preemptive, passing in the current job and then the current time. And then we're going to log the completion event. So again, I have this string pre-made here, and this is mainly just so we can see in the console. So we're going to print the current job's job name. We're going to pass in the finish time. We're going to pass in the turnaround, so the finish minus the arrival. So finish time minus the current job's theoretical arrival. I suppose you can make an extra variable for this, but I figured, not really necessary. And then finally, the absolute deadline, so the arrival plus the relative deadline. So again, the current job's theoretical arrival. We're running out of space here, plus the current job's deadline. Let us do that so we're all in view here. So next we're going to advance the single simulation clock to the job's completion time. So current time, we're going to make that equal to the finish time. And then we're going to move to the next job in the queue. So we have the case when it's ready, but we need to also simulate the case where the queue head or the current job has not arrived yet. So the CPU is going to be idle. So I'm just going to use else. And then the first thing we need to do here is calculate how long the CPU must wait for the next job. So we're going to store that in a long variable called, we're going to call it idle time because the CPU is idle. So this is going to be the current job's theoretical arrival minus the current time. Then we're going to basically print saying that the CPU is idle for a certain period of time. So we're going to display the job name, the current job's job name. We're going to pass in the current job's task ID. We're going to pass in the current job's theoretical arrival. And then we're going to pass in the idle time as well that we just calculated. And then we're going to simulate the idle time using sleep. So we're going to sleep for idle time. And then we're going to update the clock to the arrival time of the next job. So we're going to set current time to be equal to the current job's theoretical arrival. So now that we're done with that, we can actually get into the summary and analysis. So we're going to first print the total jobs that we have. Then I'm going to print out a table here, the top of a table, just so we can see the results. So we're going to, what's important here for us to see is how many deadlines did we actually miss. So we're going to declare a counter for that called missed deadlines. And we're going to make that equal to 0. And then we're going to loop through the completed job array to print out the results. So for int I equals 0, I is going to be, we're going to do this up to the total jobs. And then we're going to increment I. We're going to, first we're going to declare a job pointer, the one that we're talking about. We're going to store the arrival, and we're going to extract that from the job's theoretical arrival. And then we're going to do the same thing for the start time. We're going to do the same thing for the finish time. We're going to do that for the waiting time. So we're going to declare a long variable called the wait, and we're going to make that equal to the start minus the arrival. We're going to do the same thing for the turnaround, which is the finish minus the arrival. And then we're going to do the same thing with the absolute deadline. So we're going we're going to make that equal to the arrival plus the job's deadline. We're going to declare a constant character for status, so whether it's met or missed. Well, a character pointer called status. Then we're going to check to see if the finish time is after the absolute deadline. So if the finish is greater than the absolute deadline, which we calculated just before, we're going to set the status to missed. And then we're going to increment the missed deadlines counter. But otherwise, we're going to set the status to met. And then we're going to print out each row that we started with above. So we're going to do print F. So we're going to be printing out the job's name. We're going to be printing out the arrival. We're going to be printing out the start. We're going to be printing out the finish. We're going to be printing out the wait time. We're going to be printing out the turnaround. We're going to be printing out the absolute deadline. And then finally, we're going to be printing out the status itself. So after we go through each job, we can now print the final result in terms of the number of deadlines versus the number of jobs itself. And then in that print statement, we're going to pass in the missed deadlines count as well as the total jobs count. And then finally, we're going to clean up the mutex lock. So pthread mutex destroy. And then we're going to pass in the address of the print mutex. And then we're going to return 0. So as a review, this was a pretty substantial function. We are informing the user of the fact that we're starting. We're notifying the user of how the jobs are going to be processed. We're declaring our jobs array. We're declaring our print mutex. We're checking to see for errors here while we're initializing. We are assigning our job count or counter. We're going through the number of tasks in our outer loop, and then we are assigning the offset. We're assigning the deadline. We're assigning the burst time. And then we're assigning the period. And then in our inner loop, we're going through the cycles. So we were first declaring a pointer to the current job slot. Then we are assigning our task ID. We are assigning our cycle ID. And then we are formatting our job name. Next, we're going to calculate the theoretical arrival. And then we're simply storing, or copying rather, the burst time and then the deadline. And then we're incrementing the job count. Next, we are sorting jobs. And then once that's done, we're going to notify the user that we're done. Then now we can actually start. So we can initialize the current time, obviously starting at 0, initializing the job index, obviously at 0, and then we're going to go through our jobs. So we're going to initialize the current job, and then we need to see if the job is ready. We're going to notify the user, and then we're going to actually do the job, and then we're going to notify the user once that's done. And then we're going to set the current time to the finish time of that job, and then move on to next job. But otherwise, if the job is not ready, we want to see how long it's going to take. So we're going to calculate that and then notify the user, and then sleep for that time, and then again update the current time. So once we go through all of our jobs, we're going to print out our table here, and then we also want to track the number of missed deadlines. And then so for each job, we're going to first have a variable for the job in question. We're going to extract the theoretical arrival. We're going to extract the start time. We're going to extract the finish time. We're going to calculate the waiting time. We're going to calculate the turnaround. And then we're going to calculate the absolute deadline. And then we're going to set our status, a character pointer for the status. So if the finish is greater than the absolute deadline, i.e. if a deadline is not met, we have to update the status as such, and then add 1 to missed deadlines. But otherwise, we update the status as such. And then we can finally print out the info for that particular job. So once we get through all the jobs, we can print out the final analysis. In this case, how many missed deadlines. And then finally we destroy our mutex before exiting our program. So this was a substantial example. Now let us reward ourselves and finally compile it. Again, note we need the pthread argument in there because we're working with the pthread library. And let's run it. As you can see here, this actually simulates a number of seconds. But while this is going, I create a diagram here of our example here. So T1 is going to be in red, T2 is going to be in green, and then T3 is going to be in blue. So this first third of the table shows that. And then the second third of the table shows our periods and deadlines, which I have as equal in this example. So we're starting off with T1 because that's the first one that shows up. It has an offset of 0. T2 has an offset of 1, but it's not going to go right away because T11 is currently executing. And then T3 has an offset of 2, but that's not going to start running until T21 is done. So I hope this makes sense here. It's important. Showing it this way as well is important because here at this point, job 1, 2 is ready, and then immediately once job 3, 1 is done, job 1, 2 starts, and then in a similar way, job 2, 2 is ready, but doesn't happen until job 1, 2 is completed. And then since task 3's ready is all the way out here, job 1, 3 is going to execute. But as you can see here, we run into issues. Job 1, 4 is ready here, but job 2, 3 takes up the first second, and then job 3, 2 takes up the next 4 seconds. So once we finally get to job 1, 4, it's going to cut short because the deadline is passed. And as you can see down here, this block of time represents the time that the CPU is idle. So going back up here, we can see that there was one missed task, i.e. job 1, 4. So that makes sense there. And then we also have some CPU idle time, which matches here as well. So I hope this example in C programming was a good way of showing the first in, first out scheduling policy. It's always good to apply your example in programming. Like this video if it was informative. Comment with any questions or thoughts or future video ideas, and subscribe to the channel to get more videos like this. Otherwise, thank you for your time and have a great day.